Hello. The third type of test statistics is the criterion-based test. By the way, there is no like a unified name for this. It is called in different ways, like distance difference test, distance metric test, or some textbooks simply call this likelihood ratio test because that's the most famous test in this form. And F statistic also falls into this category. So let's think about this. We go back to the maximization or minimization problem for two different models. So now we are going to consider maximization here, but you may use minimization. Excuse me. So the unrestricted model is simple. Maximize the criterion function. I don't know what is the criterion function, but of course it has to satisfy the basic assumptions like unique maximizer and uniform convergence. And using the same criterion function, the restricted model additionally use a constraint. The hypothesis, the null hypothesis, becomes a constraint in the maximization problem. And the maximum, their maximum is achieved at these 2 points, right? Obviously, unrestricted estimator is the maximum for this problem, and restricted estimator is the maximum for this problem. Now, you may easily understand that the constraint, because of the constraint, the restricted maximum must be smaller than the unrestricted maximum because it is restricted. So you have to maximize with some kind of penalty, the constraint. So in general, the unrestricted maximum must be greater or at least equal to the restricted maximum. But we will think about this. The difference may imply something. The difference may be something. That is, so for example, in an extreme case, if the unrestricted estimator satisfies this constraint, then the constraint is not binding. So that means if the restriction is true, the restriction is true, then the restriction will be in the end, in the limit, is not binding. So the difference between these two guys will converge to 0 in the end. So of course, in finite sample, it will be small. But if the unrestricted estimator does not satisfy, breaks this restriction a lot, deviates from the restriction a lot, then the big deviation causes the shadow price of this constraint heavier. So the difference will be large. That's the main idea. So how binding this restriction is depends on whether it is true or not, whether the null hypothesis is true or not. So as a result, you may compare the maximization results. And the implementation is also simple. Maximize both and calculate their maximums and then take their difference. And it should be always non-negative because of this property. It is always non-negative. And in the last step, you have to make the difference converging in distribution to a chi-square distribution. But the problem here is, so previously I just used a quadratic form, but sometimes the criterion function itself is quadratic, like GMM. So it depends on the criterion function and the model how to standardize this difference. That's the main problem. So the standardization formula is not standardized. So later I will show you two examples. likelihood ratio test. The maximization criterion function is log likelihood function summed over I, and another log likelihood function. But so they are difference. They are taken difference, and you multiply 2. That's it. That's the standardization. If you multiply 2, you get chi-square q. I forgot the proof. I don't know why 2 is multiplied here, but just simply surprising. I don't remember why 2 is. I don't have any intuition why 2 should be multiplied. But anyhow, this is the standardization method. And as a side note, likelihood ratio test is called likelihood ratio because it's in the end it's ratio. And F statistic in the linear regression case. So also I teach this to undergraduate students. So open any undergrad textbook and study that if you don't remember what's going on. So the F statistic for a regression model takes these forms: sum of squared residuals for restricted model and sum of squared residuals for the unrestricted model. This is the basis of this test statistic. So remember, the least squares method are minimizing the sum of squared residuals. So that is the criterion function. So the criterion is evaluated at the restricted model and the unrestricted model, and we take their difference. But in this case, we are minimizing, not maximizing. So you have to subtract unrestricted model from the restricted model. So this is positive. So earlier, when you use maximization, u minus r is positive, but now in the minimization problem, r minus u is positive. And the other guys divide by q, and in the denominator, unrestricted sum of squared residuals and n minus k minus 1. These are standardization factors. So again, now I think you remember this. It is related to the real F statistic. But anyhow, I don't remember clearly why we need this. This is the standardization, quite different from multiplying 2. So there is no standard way to standardize the F statistic or likelihood ratio type statistic. And then let's think about the pros and cons. Good thing about this: invariant to the functional form restriction. So, however, it depends on the criterion function. As you see, it directly comes into the test statistic. So the criterion function may cause some difference, but restriction does not matter. And theoretically, the likelihood ratio test is the most powerful test under certain conditions, very restrictive. So it is called Neyman-Pearson lemma. It's quite restrictive, so you cannot claim this in most cases, but it is meaningful. It means something, and you don't need to calculate the variance and its inverse. It depends. So I said you don't need to calculate the variance, but you need to know how to standardize the test statistic. In this case, you only need to multiply 2 instead of inverting the variance matrix. So it's clearly attractive. So especially if Q is large, then inverting a Q by Q matrix could be costly, like computationally difficult. Then a likelihood ratio test is relatively much better, more attractive. And in some cases, in some special cases, the unrestricted model is going to have 0 in the end by minimization. Like for example, if you have an exactly identified GMM estimator, this will be true. So in some cases, then you don't need to calculate one of them. You don't need to calculate this much, this part. So it's so nice. So that could be an advantage when you use this. But the problem here is you need to estimate both. So if one of them is difficult, then you are in trouble. And maybe the main problem, whether you if you don't know how to standardize the statistic, then it may be theoretically more complicated. You need to know this to find the limiting distribution. Okay, and the final type of the test is the gradient test. It also has many different names. Some people call this a score test. Some people call this Lagrangian multiplier test, LM test. So LM test, I learned it as an LM test. Anyhow, I just call this gradient test. It's my name, different names are used. So again, think about maximization problems. Now, I will think about the first order condition of the maximization. So theta, I will define the first derivative of the criterion function as s. This name s is coming from the score function for the maximum likelihood estimator. So the first derivative of log likelihood function is called score in MLE, and I'm following that notation. So if you define the first order derivative as s, then always the unrestricted estimator satisfies the first order condition. Right? This is how you obtain the unrestricted estimator. However, it is not the case for the restricted estimator. Restricted estimator has an additional constraint. So the first order condition, the derivative of the criterion function may not be zero. Like let's think about this. Think about the Lagrangian formulation. You have shadow price Lagrangian multiplier lambda for this restriction, and this is your maximization problem. And then if the restriction is true, as I said, it is not binding, then lambda will be close to zero. So, and if the restriction is wrong, then the restriction will cause bigger problem. So lambda will be non-zero, different from zero. So then in the end, your first order condition looks like this. This must be zero. Not only the derivative of the criterion function, but additional restriction. So the score function plus something is zero, but plus something may be different from zero if lambda is different from zero. So if the restriction is wrong, this part is likely to be different from zero, causing the score to be different from zero. So as I said, this score function, score, will be zero if the null hypothesis is true. Otherwise, different from zero. This is our rationale, and you may derive the limiting distribution of the score, like from this. Say the restricted estimator follows a standard limiting distribution, and by the delta method, your new variance takes this form. Your variance following the delta method, your variance phi takes this form, and use this phi in here. Estimate the phi, of course, estimate that, and then you put score on both sides, and just and then we have chi-square q. Okay, so what is good about this? It is good because you only need restricted estimator. I do not need unrestricted estimator. So restricted estimator may be easy to calculate. For example, if your hypothesis is that many parameters are zero, for example, then that means you don't need to calculate those parameters. They are assumed to be 0. So simple. So like if the unrestricted estimator is a high dimensional, but the null hypothesis reduces the dimension, then restricted estimator will be much easier to calculate than the unrestricted estimator. So then gradient test, LM test, may be better. Also, it is invariant to the restriction. So, but also again, it depends on the criterion function because basically score function is the derivative of the criterion function. So if you use a different criterion function, your score will be different. And the problem, again, similar to the Hausman test, the dimension of V may be different from Q. So the rank of the variance always determined by Q, but the variance itself would be K by K. Then the variance may not be invariable, and you need to use the generalized inverse, which was discussed in the Hausman test. Same problem arises here. So equivalence. In the end, theoretically, all of them are equivalent, asymptotically equivalent. So all of them are converging to chi-square Q. All four test statistics converging to the same distribution. So in the end, in the limit, the difference will be 0. Or if you have sufficiently large sample size, it doesn't matter whatever you use. Just use whatever you like, whatever the easiest to compute. That's good. And sometimes the functional form matters. The functional form matters in some cases, but if everything is linear, then like there is no difference at all. If everything is linear, then there is no approximation error. So in the final sample, their numbers, the t stat t, this t and this t, and this t, and like say this say this, all the t wild test, Hausman test, and gradient test, and like a criterion based test should have the same test statistic if everything is linear. There is no room for approximation error at all. And as I said, you just choose whatever easy to compute. That's the maybe the best way to handle this. Or I will introduce some specific context endogeneity test or exogeneity test. So there are some commonly used tests. Usually their idea is based on one of the four, but there are more like they are developed under different names. Then you just use them. Like if Stata has the built-in code, use that. Okay. I will call it a lecture, and in the next video, I have some graphical explanation of these four types of tests. So those tests can be compared on graphs. I think that will help you develop the intuition what's going on. So I will spend a few more minutes on that in the next lecture, and then we will discuss some special cases endogeneity test where we would like to test whether a regressor is endogenous or exogenous. And later, and also in section 6, we will study over identification test, which means we would like to choose whether which instrument is valid and which is not. So that's what we are going to do. Thank you for watching. See you later.